This video lesson is designed to help students who are going to be taking AP Calculus with their summer worksheet, which covers pre-calculus review. Since the worksheet is rather lengthy, there's going to be more than one video to help with these. This video focuses specifically on Roman numerals 1 and 2, which is mainly about simplifying expressions. Please do not feel that you have to watch the entire video. If you would like to skip around to the different sections, that is fine. I'm just providing this to help you wherever you're having some issues. Roman numeral 1, section A is all about manipulating expressions using the exponent rules. You're trying to get it in one of two forms, either looking like a power function of a constant times the variable raised to a constant, or you're trying to get it to look like an exponential function where it's a constant times a constant raised to a variable exponent. So that's the first thing to do, is decide which of these two forms you're going for, and then you manipulate the expression until you get what you need. As we look at example 1, I think we can tell that we're going for the power function. We're looking to get it in this form because you can see that the exponents are all constants. They're not variables. So we're trying to get it as k times x to the p. And if we what I usually do is, if I have any roots, I first of all change those to exponents. So that would be x to the 1/3 on top. On the bottom we have 5x cubed. And now we can just kind of do the division. If you want to think of the fact that there's a 1 in front of the x on top, then we basically have 1 divided by 5 times x to the 1/3 divided by x cubed. And of course what we do there is subtract. So we have 1/5 as our constant in front, and we'll be left with x raised to, and let's see, 1/3 minus 3, that would be 9/3, so 1/3 minus 9/3 is -8/3. And we can stop right there. We have it, this is our k is 1/5, and our p is -8/3. I forgot to mention that the main reason we're doing this exercise is that in calculus, if you can get expressions to look like a power function or like an exponential function, then it's actually quite easy to do some calculus operations with it. Two of the main ones you're going to be doing is taking derivatives and taking integrals, and both of those are easy to do if you have it in one of these two forms. Alright, so let's take a look at number 2 now. The first thing I'm noticing is that the variable is in the exponent. So that means I'm shooting to make it look like the exponential function. And since the 2 is the base on my power there, then I guess the a is probably just a 1, so I have 1 times 2 to the negative n. So you might say, well, 1 is the a and 2 is the b, but if you look at it, we really don't want that negative up there. We just want the variable x right there. So let's deal with that negative exponent. Hopefully you just kind of remember the rule as to how to deal with it, but a little trick I usually teach my Algebra 1 students is, if you'll just turn it into a fraction, put it over 1, then the way you get rid of a negative exponent, whether it's in the bottom or in the top, is just to move it. So as we move it down, then we can turn that into a positive exponent. So it becomes 1 times, we'll be left with a 1 on top, and then 2 over n. And let's see, we still don't quite have it as just a number b to the nth power, but we know that 1 is over 2 to the n is the same thing as 1 over n, 1 to the nth over 2 to the nth, and that becomes 1/2 to the nth power, just using our exponent rules. So it looks like our a is 1, our b is 1/2, and now we have it in the form of the exponential. Alright, and finally, looking at number 3 example, we just have, looks like, let's see, it looks like we do have an exponent, a variable in the exponent. So once again, I think we're looking for an exponential function here. Let's get rid of those parentheses by squaring all of this. And of course we know that we can square every piece that's inside the parentheses. So that'd be 2 squared times, and then we have e to the 2x, and that's also squared. Of course, 2 squared is 4, and then the way we square a power raised to an exponent is simply by multiplying the two exponents. So we end up with e to the 4x. All right, and we're almost there. Just if we just rewrite, obviously, pretty obviously here, a is 4, and the b is simply going to be e to the 4th, right? This would be the same thing as e to the 4th, then to the x power. Once again, I'm just kind of undoing the power to an exponent rule, and by splitting up that product there. All right, so it looks like a is 4, b is e to the 4th, and then we have our x to the exponent. In closing here, I just want to mention how important it is to be able to manipulate expressions like these using exponents. We will be doing it a lot in calculus, and if you can do it, if you can do the algebra like this well, then it makes the calculus a lot easier. Let's see, Roman numeral 1b is all about completing the square. This is not something we're going to do a lot of in calculus, but it's one of those things you might need from time to time. So it's good to review this process. So here's our example: the 5x squared plus 30x minus 10. We want to complete the square on it. So the first step is we first need to have it just as x squared, and not have that 5 in front. And all we want to do is really focus on the first two terms. We don't need to worry about the constant, but just the two x terms. So we're going to factor the 5 out of those two terms, and that'll leave us with x squared plus 6x in parentheses here, and then we have the minus 10 on the outside. All right, and by the way, this is just an expression. This is not an equation, so you can't just add the 10 over to the other side of an equal sign. There is no equal sign. It's just an expression. All right, but we can still complete the square on it. Now that we have it factored and we just have the x squared, or a 1 in front of that x squared, then we can start to think about turning this expression inside the parentheses into a perfect square trinomial. And of course there's a little trick to it, that you always look at the middle coefficient, the x coefficient, and you take half of it and then square it. So hopefully that's something you just remember. But another way to think about it is you're just looking for the number that you can add to this expression that will turn it into a perfect square trinomial, which means that when you factor it, you're going to be able to, the two factors are going to be identical, the two binomial factors, and then you'll be able to write it as something squared. So if you think about it, if we add 9 here inside the parentheses, then of course we can factor it as x plus 3 times x plus 3, and then be able to write it as x plus 3 squared. All right, of course the quick way to figure out that it's a 9 that goes there is simply take half of the 6 and then square it. All right, now we need to be a little careful because I've kind of jumped ahead a little bit. I still have this 5 out here, whoops, in my pen, and the 5 is going to be out here. We have to be a little careful that we have this minus 10 out here, and now we've just added 9 inside the parentheses, so we need to compensate for that because we don't want to change the value of this expression. So I'm going to actually subtract 45 out here. And if you're scratching your head about that, well, by adding 9 inside the parentheses, I really added 45 to the entire expression because I had 5 times 9. And so therefore that's why I'm subtracting by 45 so that it balances it out. Now if I had an equation, yes, I could just add 45 to the other side of the equal sign, but I don't have an equal sign, so I have to just subtract, and now it'll just be minus 55 here, as well as right here. Okay, and I think we are done with completing the square. And the nice thing about completing the square on a quadratic is you can then kind of read what the transformations are. Like if this was a function here, like y equals, then we could look at it now and see that, we have a couple of shifts going on, like looks like a horizontal shift to the left by 3 units. We're shifting down by 55 units, and this 5 multiplying outside the square part is going to be a vertical stretch by a factor of 5. Hopefully that's some things you remember from Algebra 2 and Precalc. Roman numeral 1c is something we're going to be seeing a lot of this year, and that's when you have an expression, a fraction, where there's just a single term in the denominator, okay? As opposed to, you might say, well, that looks like 2 terms multiplying, but as opposed to something like this, like if we had square root of x plus 3 all over 3 root x minus 2, okay? See, that's basically a binomial divided by a binomial, and we can't do much with that, okay? But we can do a lot with an expression that just has a single term in the denominator, because we can remember that, let's see, that this would be the same thing as if you just took 1 over 3 root x and multiplied it by root x plus 3, okay? And if we think of it that way, then we know we can distribute that 1 over 3 root x, and this becomes now root x over 3 root x plus 3 over 3 root x, okay? So we're actually distributing this denominator under each of the terms here, and a lot of students will just go straight from that to here. They'll just split the 3 root x up under each of the terms and write it as 2 fractions. And of course, each of these fractions can be simplified so that we would end up with 1/3 plus 1 over root x. And if we can do this, if we can change a big fraction like this into 2 smaller fractions that are added, then the calculus becomes easier. All right, calculus is actually very easy to do if you can write an expression as a sum or a difference of two pieces. Now, if you're looking at the packet, you might say, well, this isn't exactly the answer that they gave, and if we look at the instructions, I can see that it needs to be a difference of power functions. So, a power function, remember, is written as k times x to the p, raised to the p power. Need to erase that. So I guess technically I have 1/3, that is, you can think of that as a power function. That's 1/3 times x to the 0, which is just 1. And then this would just be 1 times x to the negative 1/2, right? It's 1 over x to the 1/2, and then if I write it as a power function, it's negative 1/2. And once again, the reason for doing this is that if we can write the expression as a power function like we were doing up in Part A, it's much easier to do the calculus. Roman numeral 1d is all about adding or subtracting algebraic fractions. This is all on the lines of we may want to express something a little differently than the way it looks, so we need flexibility and the ability to do that. So, of course, if we're adding fractions, that means we need to get a common denominator, and we always look to see if, we might want to look at the factored form of each denominator, and this factor on the left would be a minus 3 times a plus 3, right? And so that means that they share a factor, and so we can just let our common denominator simply be a minus 3 times a plus 3. All right, a minus 3 times a plus 3. And so the good news is we don't have to do anything to the first fraction, but of course the second fraction, we need to multiply the top by a plus 3 also, right? So we're basically going to go a plus 3 on the top times a plus 3, and also a plus 3 on the bottom. And so the top ends up being, looks like 2a plus 6. All right, so a plus 2a plus 6 looks like we'll end up with 3a plus 6 all over a minus 3 times a plus 3. Now you may be tempted to multiply those two factors together, but I wouldn't until I know I've simplified things. So looks like we can factor the top. We can pull a 3 out. We would have 3 times a plus 2 all over a minus 3 times a plus 3. Looks like we're not able to cancel anything. Of course, we can only cancel factors. So please don't try to cancel, this 3 up here with one of the 3's down here. That just doesn't work. So we could leave our answer like this, or if you really wanted to multiply things together, we could leave it as 3a plus 6 all over what? A squared minus 9. Another very important skill, algebra skill, is to be able to undo expressions and solve for a certain variable or a certain letter in the expression. And the two examples I've chosen are a little more difficult. They're more like items 3 and 4 on your worksheet under section E. Hopefully items 1 and 2 seem fairly straightforward. Just pay attention to what you're trying to solve for. In part 1 you're solving for M, and in part 2 you're solving for A. Okay, let's see. So this example is probably more like item 4 under letter E, because we do have an exponential situation and we're trying to solve for the variable in the exponent. So of course we just want to get rid of everything else that's on this side, this side of the equation. So the first thing we can get rid of is the p sub 0, right? Let's just divide both sides by p sub 0, and we'll just be left with 1/2 equals 0.8 to the x power, right? And now we have to undo an exponential situation, which means we need to use the exponent function's inverse, right? So this is when we need to call on logarithms, all right? And you've got a couple of choices, a couple of ways to do it. So I'm going to kind of split this up. The way I would do it, and a lot of students get used to doing this, is when solving equations and you need to introduce logarithms, just take the log of both sides. All right, so if we take, and I'm going to go with, I just usually go with natural log. So I'm going to take the natural log of the left-hand side and then the natural log of the right-hand side, 0.8 to the x. All right, hopefully you're remembering your log rules or your log properties. We'll try to get to some of those as we go through this worksheet. But if we have the log of a number raised to a power, we know that power can come out and multiply the log. All right, that's basically the same property as the a power raised to an exponent, but we'll get into that in a little bit. So we'll have the natural log of 1/2 equals, and then we'll have x times the natural log of 0.8. And now that we've written it this way, it's really like a linear expression, right? We basically just have a equals x times b, and all we got to do is divide by b. So x ends up equaling the natural log of 1/2 divided by the natural log of 0.8. The other way we could handle this problem from here, from this step right here, would be just to apply the definition of a logarithm. We know that if we have an exponential situation of a base raised to a variable exponent equaling the 1/2, that would translate into the log of the base, 0.8, of the 1/2 equals the x. I think a lot of times students have an easier time thinking about it going from the log back to the exponent. We know that this expression means the base raised to this number equals that number. So, I'm just undoing that situation. So there is our answer. X ends up equaling this. Now, to get basically the same thing we have over here, we need to apply the change of base property. The change of base property says that the log of a base b is equal to the log of a base c divided by the log of b base c. Okay, this is a property that you probably haven't had to use as much with the technology advances that we've had, but back in the 80s when your teacher was in high school, he had to apply this property all the time because we couldn't raise logs to special bases like 0.8. We had to either use base 10 or base e. So you can choose, the nice thing about this property is you can choose whatever base you want to be that c number, as long as it's the same. You got to make sure you're applying it up top as well as in the bottom. And so this expression up here can quickly become the natural log of 1/2 divided by the natural log of the base, which is 0.8, equals x. And I've just chosen for e to be my base. Now, if you had wanted to use common log, that's fine. You could say the common log of 1/2 divided by the common log of 0.8. It would give you the same answer. I was just trying to match it with my answer over here. And of course on this problem, I chose to take the natural log of both sides, but if you had wanted to take the common log of both sides, you could have. I will just say, you'll see as the year goes along that working in natural log is usually easier. Some of the rules that we have in calculus will be much easier in natural log. Before we move on to the next example that's on this page, let's take just a little bit of time to review our exponential and logarithmic properties. I'm not going to get into the proofs of all these rules and so forth, but I did want to list them out here. Here's the exponent rules, and here are our logarithmic rules, and I've color-coded them. We have, the rule that says if you're multiplying like bases, then you add the exponents. Well, that means because logarithms are the inverse of exponents, then we also have a rule that is similar to that with the logarithms, where if we take the log of a product, that's the same as the log of the first term plus the log of the second term. All right, and then we have our subtraction rule with like bases when you're dividing, and if you take the log of a quotient, that's the same thing as the log of the first minus the log of the second. If you keep in mind that the logs are the exponents, are actually the exponents, then that kind of makes sense then. We're subtracting the exponents here, we end up subtracting the exponents here. And then we have our power to an exponent rule, where we multiply the two exponents when that's the case. And if we take the log of a number raised to an exponent, then we can multiply that exponent times the log of the number we're taking. And so, those are both exponents in a sense. So we're multiplying the two exponents here, we're also multiplying the two exponents here. All right, and then these rules are a little different over here. We don't really have a log rule that's similar to this, but these are just your distributive rules. It is okay to distribute an exponent over a product or a quotient. You just have to make sure that you do not, I repeat, do not do it over a sum, right? Or a plus or a minus b raised to the c power does not equal a to the c plus or minus b to the c. Please don't do that this year. You are calculus students. You should have the algebra rules down and not make mistakes like this. Likewise, I've also included a rule, the fourth log rule, which is the change of base rule that we were talking about earlier. Okay, so most students are pretty good with the exponent rules. They work with exponents more than with logarithms. They have a little more difficulty with the log rules. Just keep in mind there's only 4 rules, and the first 3 are the ones you use most of the time. So that's not that many rules to remember. Pretty soon we're going to be moving on and simplifying trig expressions, and the trig identities. There's a lot more trig identities than there are log rules. So kind of keep that in mind. It's just 3 of them for the most part. All right, so looking at this example, we're trying to solve for y, and maybe the conflicting part here is the fact that we have y on both sides. So of course, maybe a very natural step would be, think about it this way. If we're going to end up with y equals some expression, we need to get all the y's on the same side. So let's just go ahead and subtract that minus ay over. Okay, so we'll have by minus ay. And then, you know, that d, that negative d, we could just add that d over to the other side. We want to get the y's, all the y's on the same side, and all the other numbers on the other side. So I'll just end up with by minus ay equals c plus d. All right. Now this is where a fair number of students have a little difficulty trying to figure out how do we, you know, separate the y's or get the y by itself. Well, let me show you a similar example, because you've seen this before. This is really just a linear equation if you think about it. It'd be the same thing as if we had, say, 5y minus 2y is equal to, you know, 3 plus 4. All right? You know, and you know that what you would do here is just combine the y terms and call it 3y. Okay? Well, really, when you combine the terms, what you're really doing is you're factoring the y out to the front and then just subtracting the 5 and the 2. Okay, so what you really are doing is you'll end up with y times 5 minus 2 equals 3 plus 4, and then you simply divide by the 5 minus 2. So you end up with y equals 3 plus 4 divided by 5 minus 2. And we're just going to do the same thing over here. It's just that we can't, you know, we can't combine these two terms and call them 3y like we could over here. So we're just going to factor out the y, and then we'll be left with b minus a in parentheses equals c plus d. And now we can just divide by the b minus a, so we end up with y equals c plus d divided by b minus a. I just want to mention a couple of other things about this equation, just to emphasize, first of all, that this is just a linear equation. So all you really need to do is get the variable you're solving for on the same side of the equal sign, get everything else over to the other, then factor that variable out and divide. And we will see situations like this throughout the year in calculus. I also wanted to mention that it's possible you could have ended up with a different answer, or at least an answer that looks different. Instead of subtracting the ay over, if we had subtracted the by over and then subtracted the c over to the other side, we would have ended up with, you know, y equal to something like this, negative c minus d all over a minus b. And, you know, if that happens, just keep in mind it's really the same answer. You know, all you would have to do is multiply by negative 1 over negative 1, and that would give you this answer. And, of course, that's not changing the value of our answer. Hopefully you're getting the message that it's important when doing calculus to be flexible with your algebraic expressions. You need to be able to rewrite an expression to look a little differently, and that's what we have here. Now we're getting into trigonometric expressions. All right, so we need to be able to use all the identities, all the rules we know, you know, the basic ones, to be able to write something a little differently. So here's a couple of examples. We just want to simplify this expression. It's not an equation, just an expression to simplify. From what, you know, one of the big tips I usually tell my pre-calc students is when you see some operation happening here, it's good to just go ahead and carry out that operation. So they're asking us basically to subtract these two fractions. So okay, let's subtract the two fractions. Subtraction of fractions means we need to get a common denominator. So we're just gonna, the easiest way to have a common denominator is just to multiply the two denominators together. So we'll have sine alpha times cosine alpha, and then we'll do the same thing over here. Sine alpha times cosine alpha. And then, of course, on the first fraction, we're going to have secant alpha times cosine alpha. And on the second one, we're going to have sine alpha times sine alpha. This is looking more complicated, but let's see if we can get some things to happen. First of all, you know, these two fractions, we can now combine them into one. And some students would just do that, you know, kind of skip over this middle step that I did right here and just go straight to a single fraction. But let's see. Secant alpha times cosine alpha. Well, secant alpha we know, right, is 1 over cosine alpha. So it looks like happy things are going to happen there. And then of course sine alpha times sine alpha is just going to be sine squared alpha. So it looks like we end up with 1 minus sine squared alpha all over sine alpha cosine alpha. And hopefully as soon as you see that square, you're thinking, okay, it's a good chance we can use a Pythagorean identity on this, right? That involves the squares. We know that cosine squared of alpha plus sine squared of alpha, I'll write it over here, so we know cosine squared alpha plus sine squared alpha equals 1, so therefore if I see 1 minus sine squared alpha, I can replace it with cosine squared alpha. So that's over sine alpha cosine alpha, and now my cosine alpha in the bottom can cancel with one of the ones in top. So we're left with cosine alpha, I put a theta there, cosine alpha over sine alpha. We know that is going to give us cotangent alpha. So what were some of the strategies that we used to simplify this? First of all, we recognized the main operation was subtraction, so we carried that out. Within that, we saw that changing to sine and cosine seemed to help, like changing a secant or something like that to sine and cosine helped. Another strategy, when we saw squares, we thought Pythagorean, and that allowed us to simplify things even more. So those are some of the things you want to think about as you're simplifying trig expressions. All right, now going over to the other example over here. First thing I'm noticing is that we have double angle expressions here. We've got sine of 2x and cosine of 2x. So our double angle identities will probably come in handy here. And the ones for sine and cosine you should know. We use them enough. I mean, it's not going to be all the time, but we do use them. So we know sine of 2x, our double angle identity for sine of 2x is 2 sine x cosine x times cosine x. All right, and our double angle identity for cosine of 2x, let's say we have a 1 plus. Well, we've got a choice with cosine. You know, we could go with either cosine squared x minus sine squared x. And there's other forms of this. If you want to replace the cosine squared x with, if you want to replace the cosine squared x with 1 minus sine squared x, you can end up with 1 minus 2 sine squared x. Or if you replace the sine squared x with 1 minus cosine squared x, you end up with 2 cosine squared x minus 1. So we've got a choice. I think I might just go with the first one. You know, let's see. Maybe we might come back and say, well, it'd be better to use a different one. But let's go with 1 plus cosine squared x minus sine squared x. And since that's just a 1 plus, I'm not even going to bother to put parentheses around the cosine squared x minus sine squared x. All right. So can we do anything with this? Well, one thing I'm noticing is we've got some squares in here, so maybe a Pythagorean might relate here, and I think I see on the bottom we could have a 1 minus sine squared x. And so if we put those together, here I'll take an extra step. So we have the 2 sine x cosine x, and then we could put them together. So we have 1 minus sine squared x plus cosine squared x. And that 1 minus sine squared x becomes a cosine squared x. So we just end up with basically cosine squared x plus cosine squared x on the bottom. So we'll have 2 sine x cosine x, and on the bottom we'll have 2 cosine squared x. And now we can cancel some things, right? Because we have factors. So the 2's can be canceled out. And then this cosine x can cancel out with that cosine x. So this time we end up with sine x over cosine x, which is just tangent of x. That was an x, by the way. Now that we are at the end of the simplifying sections of the worksheet, just wanted to point out that the types of functions that give students the most trouble are what we call the transcendental functions. And the main ones that you studied in precalculus were the exponential log functions and then the trig functions. So what this means, what a transcendental function is a function that transcends the normal rules of addition, subtraction, multiplication, division. And so because of that, you actually have to learn some special new rules to help you deal with that. A good example of this would be with the distributive property. We know with many functions we can distribute a variable or a number, or say some expression, over parentheses when we're multiplying. So like if we had 5x times, I don't know, 25x squared minus 4, we can get rid of the parentheses and simply multiply the 5x by both terms, and of course end up with, 125x cubed minus 20x. But you see, we can't do this with logarithms. You cannot distribute the natural log over parentheses. So if we have the natural log of, say, x squared minus 5, this does not equal the log of x squared minus the log of 5. Okay, in fact, there's really not much we can do with that. We also can't distribute natural log over a product. Like if we had natural log of 5x squared. This would not equal the natural log of 5 times the natural log of x squared. What does it equal? Well, we know that it equals the natural log of 5 plus the natural log of x squared. So you see, that's a special rule that we have to learn when we're dealing with logarithms. It does not work the same way that we're used to with addition and subtraction, multiplication. Right? We see the same thing with the trig functions, right? Which is why we have to learn all these new trig identities. All right? And the ones that are probably most important to know are these first three. You definitely need to know the basic trig identities that allow you to change expressions to sine and cosine. Along with those might be, knowing that tangent is the reciprocal of cotangent, or that, cotangent equals 1 over tangent. Those are important rules to know. It's important also to know the Pythagoreans. We do run into a lot of situations that involve squares of sine and cosine and so forth, and so it's good to know those. And then I throw in the double angle ones. They show up often enough that it's good to be familiar with them. All right, and if you can if you can hang on to the sum and difference identities, those are good too. Those are ones that show us that you can't distribute a sign across addition like we could with multiplication. For instance, we have the sign of, say, alpha plus beta. Okay, that does not equal the sign of alpha plus the sign of beta. All right, what does it equal? Well, the sum formula tells us it equals the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. All right. If you're having difficulty with those, Mr. Whipple, I can teach you a cheer that will help you remember them if you'd like to learn it. All right, so that does it for this first video that covers Roman numerals 1 and 2 of the worksheet. If you're looking to move on into the other parts of that worksheet, check out the next video.